Okay, can you guys hear me all right? Okay, so welcome to the presentation of Luna. Very quickly, what we are gonna touch upon. So this talk essentially has three parts. The first one is more philosophical, and when I try to talk about the problems in software development that we have spotted. The second part is mostly about Luna, how Luna tries to be a solution to those problems, how it's constructed, and then a more technical overview of Luna for those of you interested in programming languages. And if you don't want to listen to that, you can leave, and I won't be mad. Okay, so to start off, I would like to tell you an anecdote. And it was around the year 2000 when my mom was she was teaching a Haskell class at one of Krakow's universities, and pretty much everyone was laughing and no one was taking the class seriously, right? It's Haskell, it's functional programming. What good is it for? You cannot use it. It's just, you know, the playground of academics. And look at us. Here we are on a conference. One of the tracks is Scala, functional programming. It's the hottest topic. So the moral of this story is that it may be really hard to predict what's going to catch traction, what paradigm is going to prove successful, and perhaps the landscape may change so that you will start needing different solutions and different mindsets. And another lesson is that we really need to keep trying and keep our minds open, because we don't want to get stuck in local optima. Just like, you know, the birth of functional programming, it was, people thought it's ridiculous, but then we started having problems with concurrency, with correctness, and suddenly it's very hot. So please listen on. Right, what are some of the problems with software development? First of all, we know for a fact that the number of the amount of data we are producing as a humanity, as the industry, is constantly growing. If you look at the graph, it's more or less exponential growth. It's not a very scientific way to put it, but more or less it's growing exponentially. So the next thing we know is that we are only able to actually make use of, to process, a very small fraction of the data. As of 2015, it was 0.5%, so a lot of unharvested potential. Now, as we are trying to process the data, we keep creating more and more programs, and the programs are more and more complex. Now, this complexity is starting to get problematic, because we are no longer able to actually fully comprehend our creations and to kind of comprehend them in full. So if you need an example, that's the meltdown inspector bugs in Intel processors, that, you know, something everyone was taking for granted. It just works. This is the processor. It works. But then someone spotted a bug, and suddenly everything is falling apart. Now, next thing is that we are using a lot of tools, a lot of great tools, video processing tools, visual effects, 3D modeling, you name it, right? But the tools themselves are hard to grasp, hard to learn. And if you learn one, you don't necessarily can transfer this knowledge to another. Then when you're programming, it's really hard to look at the code, look at the system, and say what it does. You just look at a spaghetti of code, and this is why people are drawing diagrams too. If you have a large system, you want to kind of capture the idea inside a diagram, and then, you know, you can show it to someone who will understand. If you show someone, you know, look, here's my service, it's 2,000 lines of code, pretty much no one will be able to tell you what it does, right? The next problem is that right now, the industry is using programmers as kind of translators. There's the domain knowledge, the problem you're trying to solve, and then there's code, and you need something in between. And the programmers, what they are doing basically boils down to translating this, right? So it all boils down to communication. And I would like you to look at a certain dichotomy. So on one side, we have a domain expert, say someone who is an expert mathematician, expert biologist, and he's working on a product that processes some biological data, say, right? And he has all the knowledge required to solve the problems. He is actually interested in the problem. He likes working on the problem itself. And he may or may not be a programmer, but he doesn't need to be a programmer. And on the other hand, you've got a programmer who is an expert coder. He likes to code, and he has fun implementing and designing technical solutions. But if you see, there's a gap in the middle. They don't really have a good language to communicate. That's why you have all the meetings, all the plannings, and so on. So one of the main things we are trying to address is to improve the communication. And the communication may actually take place on several layers, but first of all, between team members. So like, say, one programmer to another, right? Then between teams, business needs to communicate with product, and product needs to communicate with the development teams, and so on and so on. They don't have a common language necessarily. And then the fun one is between the programmer and his own code. So raise your hand if you ever looked at your code after a month and you didn't understand what you were trying to achieve. Yes, perfect. Self-awareness. So those are the problems that we see and that we are trying to solve. And the way we are trying to solve it is by building a visual, textual programming language suitable for data processing, but also general purpose programming. And I would like to show you a simple demo. Now I don't know how to play it with this thing, but okay, I'm gonna play it step by step to tell you what we are doing. And this is a fairly straightforward workflow. What we are trying to achieve here is the city of Krakow is kind enough to make public the data about all the trams, about all their locations. So we are trying to display a map with the trams in real time. So first of all, we are taking the tram information from a given endpoint, this TTSS. We are parsing the response as JSON. Okay. Now on this JSON response, well, we can inspect it. You see it down below, but we want to look up the vehicles, and here you can see that it's visualized in real time. You can inspect it. This is much like the Jupyter workflow, but aligned very differently. Okay, let's take a closer look at the stuff returned by the endpoint. I mean, that's what you do in real life, right? The endpoint returns something. You need to take a look at what it does. Now, we only want to use those cells that actually have the geographical information. So we look up something, the longitude, and check if this is just. If you don't know what the just concept means, if you know Scala, this is the option type. If you know Haskell, this is the maybe type. So we are only taking the entries that actually have the latitude and longitude. Okay, see, it looks much better. And I would like to stop you there, because here, what we have done is we have taken everything we have programmed so far, and we have collapsed it into a function, right? It does something, but we no longer need to be concerned with the internals. Now we are just happy with the function and that it works. Okay, so if we have the list in the form that we want, we can take the first element, the head, and see what's inside and try to actually transform it into a format that's understandable by the map visualizers. Okay, that's the first object. Let's see what the longitude is. See, it shows below the node. Now we need to transform it because it's in weird units. Okay, we have the longitude. That's good. Now the latitude. Okay, convert it again. Very well. Now we have the geographical coordinates. The remaining thing is to look up some information about the tram so that we know its name, so we know what to display. And those are all JSON lookups, very simple thing. Now, we want to create a JSON with this information, so we start off with an empty map. We insert the things we have just extracted from the big list. Okay, and we convert it to JSON. We have a perfectly valid JSON object. Now, this is some bookkeeping required to actually make it understandable by the map visualizer, but it's pretty straightforward. Okay, so sorry, I need to fast forward a bit. We have already seen this, but I clicked in the wrong place. Okay. Perfect. So if you take a look now, we have a perfectly valid map location that we can display. That's good. We have done it for one entry from the list, from one tram. Now we want to generalize it into a function that basically takes this information and transforms it into the GeoJSON feature. So instead of taking the first element of the list and applying this function, you basically want to map it over the list. So this will be the cool part. Let's zoom out a bit, take all the logic we have created, and now watch. We will collapse it into a function. So now instead of applying it to only one element from the list, we can map it over the list. Actually, each is a version of map, for each, if you're familiar with Scala. And very well, we have a list of all of the locations with tags. Some simple wrapping. Perfect. Now, what's remaining is to perform it every 3 seconds, the whole calculation, and boom, we've got trams in real time. Now, what's the benefit from all of this? First of all, this is the data processing that looks like data processing. That's more or less how you think about data processing. Some data flows, and you apply the transformations. It's very easy to kind of branch off from the main data flow to do some experiments to actually inspect the data, but your data flow is still intact, right? The next thing is what I already talked about, but collapsing nodes into a function. It's very important that we are able to view the code on different layers of abstraction, because the product manager doesn't need to know the nitty-gritty implementation details. He just wants to know what the product does. So the benefit from this is what I like to call manageable complexity. You don't need to actually know what every part of the product does. You need to know what all of the things do, and if you're trying to inspect one element, you should be able to do so by zooming in. And in our opinion, this enhances correctness, because you have less cognitive strain when trying to grasp the whole thing, and this enhances productivity. And now the very cool feature of Luna, and kind of the selling point. When you enter something in the graphical editor, it shows up in the code. And when you do something in the code, it's actually reflected by the nodes in real time, and that's the compiler that does the translation. Kind of think like drawing the diagrams for you. So this is the missing communication I was talking about. This is translating from the code universe into the ideas universe. Okay, so I often hear a lot of misconceptions about Luna. I hear, oh, it's like Scratch, but then, oh, it's Lua, right? it's not. So I wanted to clarify that, what Luna is not. It's not a toy. It's nothing like Scratch. By the way, Scratch is visual programming, but you're just actually assembling purely imperative instructions together. We are doing data flow, we are doing functional, it's a different thing, and we are 100% serious. Although we like to think Luna is fun to use, right? This is not some domain-specific tool. So the problem with a lot of visual solutions is that basically the visual part is an overlay over a predefined set of functionalities, be that signal processing or data processing, but we are not that. We are the common language on top of which you can build your solution. But it's not, it's not predefined to do only one thing. And then it's not the next version of Jupyter. Even though the workflow is similarly interactive, but the experience you end up getting is completely different. You don't need to scroll up and down, and your visualization don't mix up with your code. So it's a different experience. Okay, now for the more technical overview of Luna as a language, well, because when we were designing the visual language, it entails certain requirements. So the language was from the ground up designed to have dual representation. So some of the decisions that were taken actually stem from the language needing to be easy to visualize. What we want is to use static typing, but to be able to perform the computations very dynamically. So think Haskell safety, Python convenience. And yeah, we like to be the glue code for all your existing solutions. So we are integrating a lot with foreign code like OpenCV or BLAS. One remark about the type system. It's there to help. So oftentimes people think of the type system as the necessary evil or something that you need to fight with. Well, we strongly believe that it's there to help, it's there to enhance the productivity, it's there to guide you, because some of the ways you can write the program are just wrong. So the type system should eliminate them from the beginning. And of course, it should promote correctness, because we want to write correct programs, and sometimes a mistake can cost a lot. And it's so much better if we can spot it earlier. And then it can save time. If you think about running a huge pipeline that down in the middle contains an embarrassing error, like passing a string instead of an int. If it's a dynamic language, you will learn that there's an error after like 3 hours of running the code. If it's statically typed and type checked beforehand, you will know instantly, saving 3 hours of time. So the type system that we came up with is strongly inspired by Haskell, because, well, we are all Haskellers and we really like Haskell's type system, but we are also aware that it may lack user ergonomics, so it's not always convenient to type your programs. What it also lacks are objects, but I'm not talking about object-oriented programming. I'm just talking about accessors having the scope of the object they're applied to, not the global scope like in Haskell. I'm going to touch upon that later. And we really do like algebraic data types as the way of expressing data structures. So can you see the code? Well, this is a definition of a simple data type with two different variants, two different constructors. This is like a case class in Scala. I wanted to compare it with Scala because you can see that the amount of bookkeeping and boilerplate is a bit lower, and of course, this is an example that I came up with. So this is where we are much better. But in general, we try to be as user-friendly as possible. Like I said, it's like Python user-friendliness, and Haskell's type safety. This code here, I think I have a, this code here declares a data type that of type foo that can be one of two things, either a foo or a bar. And this variable here can be anything you want. So then we have a function that pattern matches over values of type foo. If it's foo, we do this. If it's bar, we do this. And in Scala, we do the same, but we have to, well, we have to construct this trait, which is, well, that's a bit of the boilerplate we would like to avoid, ideally. The compiler should be able to figure this stuff out. Okay, so I cannot help but compare this to Haskell. I don't know how many of you actually know Haskell, but our ADTs actually work as you would expect. They work like objects in object-oriented programming. What's important is that even though we have objects, we do not have inheritance. We do not have subtyping. Well, it can get messy, and everyone tells you to use composition either way, so why include this? Next cool thing I wanted to show you is how we achieve the Python level of user-friendliness actually running very type-safe and statically typed code under the hood. And this is row polymorphism. You know how in Python you basically can make a function that takes some object and then calls a method foo on this object? This is duck typing, right? And we can also make this in a statically typed world. Now, suppose we have 3 classes, 3 data types, and each of them has the name in one form or the other. And then we make a method that says, well, give me anything and return its name. It's not very easy to do in Scala, for example. I mean, it's possible, especially using Dotty's fun features, but it's not very straightforward, and it just should work, right? It's expected that the objects have names, even though you don't declare it very explicitly. You can see that we are declaring a few objects and then create a list of their names. It just works. Well, so the type of this function is actually quite involved. This is the row polymorphism. Basically, it says for any record that has a field name and also something else, give me this name. But the important part is that you don't even have to know this. It will be statically checked and enforced, but you don't really need to learn about row polymorphism, which is really important given the target audience of people who are not necessarily passionate about type systems. Now, one fun feature, it's the dot, right? Very small operator. One disclaimer, because it used to cause some confusion. This dot works like the dot in Scala for accessing fields. It's not the Haskell dot for composing functions. So we have 2 variants of the dot. One is with spaces around, and one is stuck together with its operands. And all it does is actually change the priority of the operators. So if you write some expression, possibly very complex, then write space dot space some property, it translates into this. It basically will extract this property out of the whole thing. If you stick it together, it will be parenthesized as follows. So this is an example of a language feature that sounds very silly and not really useful, but basically in Luna we don't ever need to write any parentheses. This is an example that fetches tweets from Twitter, and you can see that even though it chains a lot of functions, you don't need to write parentheses, and you can guess what it does, right? Every 5 seconds, fetch tweets from the Twitter app API, And on each fetch tweet, you just process the tweet. The same goes for HTTP requests. We can achieve, the Python requests level of nice API without resorting to default parameters. Okay, something that I didn't know whether to talk about the computational effects and how we handle this on a conference about data processing. But I thought, why not? It's important because, well, we are lazy. Our data types have lazy fields. So if you write something like this, it won't print anything. It will be deferred until you actually use the field. This is something Haskell does. Our functions do not use their arguments until they are necessary. This is important because if is a function like any other in Luna. It just takes 3 arguments, 1, 2, 3. If we did force all the arguments at once, this statement would print both things. We obviously don't want it to do it, right? So only when we use one of the branches, it will print something. This is the mechanism called call by need. So we don't use anything until it's necessary. This is quite important because, for example, it allows us to write beautiful abstractions. So if you look at implementation of a stream in Luna, it's 2 lines of code. And the API is very similar to the API on lists. You don't need to do any magic, any iterators, generators. It just works. But then we know Haskell, and we know that the laziness somehow can get confusing. So we wanted to give users all the benefits of lazy semantics, but at the same time, we wanted to make it as clear as possible whether something will be evaluated or not. And that's another part of the magic that goes on behind the scenes to keep it type safe, but the user is presented with a really nice and intuitive interface. So you can assume, writing Luna, that each separate line will get evaluated. You will never, see some print statement never getting executed because of the laziness. No, it works like you would expect. So a few examples. This. So wrapping the function reading from standard input in a data type will never do anything. It's only when you try to access it, it will print something. The same with functions, right? Const is a function that simply returns its first argument. So in this example, it doesn't print anything. Well, you can look at the implementation of these 2 functions to actually get the feeling for the laziness of arguments and strictness of lines. This function will simply return A and not do anything with B. And this function will explicitly perform A, perform B, and return B. Now, in the example with trams, you have seen the each function. It's like the difference between map and for each in Scala, more or less. So if I say list of strings map print, it won't do anything. It will return a list of thunks. But if I say each, I can be sure that it will perform the action on every string without any laziness. Okay, quickly wrapping up. The state of the project is that we have recently, at the beginning of the year, released everything and open sourced it, so any contributions are welcome. It's a very interesting code base, lots of Haskell, some React. You can learn a lot, and any contributions are welcome. We could use any help. What we are working on now is the performance. So I would say if you download Luna now, it's working okay. If you download it 2 months from now, it will be 10 times as fast. No, really, it's lots of work. We are working to make the type system even more expressive and even more user-friendly. We are developing some libraries. So Right now, Luna has some nice stuff built in, like handling JSON, handling HTTP, handling message pack, authentication, stuff like that. Library for time, lots of nice stuff. The geographical APIs to visualize stuff on maps. We are adding some more nice things, like the recent addition is integration with OpenCV, so people are recognizing faces on images with Luna. We are doing some linear algebra connecting matrix libraries. It's all very, very nice, and it's changing quite rapidly, not in an API breaking kind of way, but developing and moving forward. So I encourage you to get in touch. This is our GitHub org. This is our website. I really encourage you to visit our chat. It's Discord, and we are always happy to chat with people who are willing to ask questions or contribute. And we also have the forum with some more in-depth discussions. So thank you. I think that's it.
Well, thank you, Piotr. Great presentation.
How do you represent in the graphical form of the language some more advanced features like higher order functions or parametric polymorphism?
I can show you. If you come to me after the talk, I can show you. But yes, you have seen examples of using higher order functions. It's not visualized very conveniently. It's just basically the text above the node contains like dots for the arguments and actually saying what it does with the function. But if a function is a value like any other, so you can create a node whose value is a function. And then if you want to pass it to a function that accepts another function, like map, you just drag it and connect it like with any other value. It's just not, it's not visualized in a very fancy way.
Cool. Another.
I have two questions. One is, can non-functional programming find value in Luna?
Of course. If I made it sound like this is only for functional programmers, that's my bias, because I like functional programming. No, it's our target audience that's not functional programmers. It's people who are domain experts, people who don't necessarily need to have knowledge about programming. I mean, you can dive into the features of the language and actually have fun, using the language in its textual form. But the regular use case, the everyday use case, is that you actually go visual first. So you don't really need to know anything about functional programming. It is functional programming because of the way we have designed the nodes and how data flows inside. But it's also a very natural way of processing data. So you will, like in the regular use case, you will never know that you are doing functional programming because you will be doing it visually and very naturally.
You've also said that it glues other programming languages. I would like to know how it does that, and also what about the databases? What databases does Luna support right now?
Yes, right now this is a work in progress. Right now we have C FFI, and everything you can call through C. We are planning on adding JS and Python support. But when I was saying that this is a glue code, it's that binding to another languages. Right now it's C, so well, it is what it is. But it's a huge set of libraries like OpenCV, like BLAS, like you name it. But then it can also serve as a glue code. For example, if you have a lot of services, you can communicate with them over HTTP. But when you encode it with the nodes, and it's the nodes that make the request, you actually start seeing how the data flows. There was a second part of the question that I don't think I answered. Cool. I think, well, for sure there is a Postgres wrapper. It's not like our main concern is that we are actually counting on the community. You know, if you need a certain database, it's fairly straightforward to create a wrapper. We have needed Postgres, so we created a Postgres wrapper. And I think there was a CouchDB wrapper because we needed CouchDB for a while. So that's the two. But you know, if you want to create one, get in touch on Discord and we'll show you how to do it. It should be, you know, like a day of work. And
Piotr, do you have huge touch screens or some VR headset in the office to play around with the data, with your hands, or?
No, we have an iPad Pro.
Okay. Yes.
Can you somehow describe why do you think that the closing the functions in nodes and all that cool graphic stuff that looks really cool, but how is it better than just having clean code? Like, I don't have extract method keystroke stuck on my keyboard, and most of my code is not a spaghetti code. And I'm closing a lot of stuff, so it's simpler on very high level. So what is the real advantage of your approach, other than looking really cool?
Yes, the answer is actually two parts. The first part is that your code is clean, most code is not, and we would like to have a, you know, like software-backed way of achieving the clean code. We think that it's very natural that you start working on something, you do all the complicated stuff, but then when you're ready to use it, you just automatically, you don't need to refactor anything, or you don't need to, you know, explicitly make it clean. You just collapse it into a function, and then that's the level of abstraction you need.
But you can do it in any integrated development environment, and people are not doing this. So why would they do this in Luna? How we can defend against 300 nodes of monster spaghetti graph instead of monster spaghetti code?
Oh, I think that's touching upon very philosophical registers, but when it's visual and the people who are working with it are not, you know, enjoying writing lines of code and perceiving their productivity this way, they actually like to keep it clean. If your nodes, you know, stop fitting on a screen, it's a natural tendency to collapse them into functions.
You think that is a natural tendency, but as you said, the people are writing bad code, even though they see the code that they write.
Yes, but when you think about the domain expert, the way he works, he doesn't want to write code. He wants to solve the problem. The programmer wants to write code. Well, it's...
And here's my small remark that perhaps you are kind of confusing or trying to prove that programmers can be domain experts and don't want to be domain experts. But we have things like domain-driven development that kind of require you to become a domain expert. And I think that many programmers, including me, enjoy understanding domain that they are trying to model in their code. So
that's true. On the other hand, there's only so much your brain can handle, and if the problem is really complicated, you know, you just cannot grasp everything. You need to remember to write the clean code. You need to remember to, you know, write efficient code. You need to remember to meet your deadlines, and then you need to become a domain expert. Well, it just takes time.
And how Luna fixes that? Because, okay, if it's a good tool, then perhaps you can do it faster, like coding.
That's one. That's the enhanced productivity.
Yeah, but
I was
we are
mentioning.
already doing it in many languages, providing better frameworks, better libraries, creating better languages.
I agree. It's a bit of a shift of responsibility. You start the domain experts actually creating the product. So say a biologist is starting to create the product, and well, perhaps he won't be, you know, hand tuning the FFTs inside the code, because that's where, you know, a programmer will step in, look at the textual representation and you know, and do the work. But it shifts the actual load more towards the domain expert, and this is closing this communication gap that I was mentioning, right? It's, well, if a guy spent, you know, several years getting, you know, masters in biology, then a PhD, then a postdoc, he won't be able to transfer all this knowledge onto a programmer, even using best practices. You know, he won't be able to do it in 2 weeks, right? But he will be able to come, use a really intuitive tool, kind of like sketch his idea. And if if it lacks something in terms of, you know, good code or otherwise good practices, that's where the programmers can step in.
Okay, so I'm sure those guys have pretty good arguments against all the issues that you raised. So I strongly encourage you to go to GitHub, fork the project, open a couple of issues, you know, address all these things, because that would be then really helpful to the guys actually working on the project, right? So I think we are out of time. You can catch them up later during the break. We're gonna have short break, but thank you very much, Piotr, once again for taking the time.